Professor Anthony Atkinson of Imperial College, London, UK. For understatements, he has declared that he doesn't want me to detract from your and his precious minutes. So the floor is yours, Anthony.
Thank you. I didn't think I put it quite like that. I'd like to thank the organizers of this conference for inviting me to such a pleasant place. I was really looking forward to coming here. Tampere was described as the Manchester of Finland, and I remembered the last conference I'd been to in such a place, which was in Poland, which is to say Manchester. One of the characteristics of Łódź was that the beer ran out every evening. It's what's called a plan. It hasn't happened here yet. Oh, thank you. I would like very briefly, using this nice pointer which I was given at the summer school last week, there we are, to talk a little about regression and unmasking transformations. What I am concerned about are methods for looking in sets of data at outliers and influential observations. Over the last 5 to 10 years, a lot of methods have evolved for this problem in regression analysis, that one considers the effect of deleting single observations, looks at the effect of that on the inference. There will be a statistic T, one deletes an observation, and this statistic changes. It might well be, for example, an estimate of a parameter, or it might be one of these instances. What I mean, what is generally meant by masking, is that single deletion methods may fail to detect important subsets of the observations. There may be groups of observations, or there may be some observations, on conclusions to be drawn from the data, and that these are not evident. These are not revealed by single deletion methods. Kind of thing that one analyzes in regression X, and there are several outliers, so that what one actually observes is that, and what one wants is some method that will reveal. I emulate Professor Box in his handling of these bits of transparency. This was inspired by one of his many years ago. Or, again, have this, and what one wants at least is to know that there are two separate groups of data. And perhaps to say that you've got that as well. There may be some factor in the data that you've forgotten to look at. In those little examples, it's quite clear what one should do. I mean, you can just plot y against x. Always, I mean, in talking about these things and writing about them, people tend to use kind of used there. But of course, the problem is most severe when you've got a large number of explanatory variables, where you can't just look at marginal plots of one or two variables, because whatever is there may be hidden. Of course, extend these deletion methods to subsets of M observations instead of looking just at the value of T and then of the effect of observation at a time. One can in fact delete M observations. So here we are, T sub K I, I've deleted I observations. Then in fact I've got 30, and I want to delete all subsets of 4 observations. Then there are in all, I think, 27. That's clearly rather exploding. Statistics is supposed to be about the reduction of. That's a splendid way of moving briskly in the opposite direction. And of course, it may not be 4 or 5. It's clearly, again, something else. What I want to is a two-step solution to this problem. The two steps, those of you who came to Professor Welch's talk yesterday, some of the things I'm saying are rather similar to the things he was saying, but I'm going to apply it to transformations. I want a two-step analysis. The first is an exploratory analysis in which the M outlying observations will be at least tentatively identified, and then the second stage will be a confirmatory analysis in which it's checked, the importance of these M suspect or different observations are checked to see whether in fact they belong to some different group or something. And what I shall use for the second stage is a variety of least squares regression diagnostics. What I shall use for the first stage is a method of robust regression called least median of squares. It can asymptotically cope with approximately 50% data which don't come from the model which is being fitted. Suppose, just to describe this, suppose I have some parameter vector b. This is just a set of numbers, okay? So for any b that I choose, then there will be a set of residuals which will depend upon b. In ordinary least squares, that vector of parameters b is chosen so as to minimize residuals. In least median of squares, instead of minimizing the sum of the squared residuals, b is chosen to minimize the median of the squared residuals. Or, of course, values, it doesn't matter. The analogy with least squares is clearest if one talks about squared residuals here. So what one wants to do is to find the value of the parameter estimate which minimizes the median of the squared residuals. Here is a little picture which shows why this might be a sensible thing to do. I have, as I had a few moments ago, I have a set of data running up here following some kind of line, and I have a different down here. One set of data very much of this sort that Colin Mallows at Bell Labs had acquired was the length of time to run a computer program. This was something to do, or to develop it or something. No, to run it. Sorry. This along here might well be some measure of the length of the program, and this would be the time. The longer it takes to do, except if it's so complex that it doesn't run, you get times down here where the program crashes. Right, well, what I have here is a purple line, which is the least median of squares line. And if you just look at the picture, I think you'll see that the median residual from this one, which will be one of these little distances somewhere or other in here, is much smaller than the least squares line. The least squares line will tend to go somewhere or other down here. And the median residuals will be larger, although the squared residuals will be smaller, because this line, the squared residuals, these ones. Well, that's the model that one wants to fit, and the algorithm that is to be used. How actually to implement this? With least squares, of course, one just differentiates and solves some linear equations. The only algorithm that seems to be successful at the moment for this problem is a Monte Carlo minimization, where it's been described as example what Hawkins and his colleagues have called elemental sets. That is, just at random, take p of the data, so that's p cases, the x's and the y's, then one can exactly fit the model with p parameters to those p observations. So you get an exact fit for these p. There's the parameter, and there will then be p zero residuals. There'll be an exact fit through the p algorithm. Then stage is, well, you find keep sampling, and for each sample, each j that's drawn, the median and find the take fitted the line for which this median residual is minimized. Well, questions on how many samples. I take of residuals emerges. That's when doing regression analysis. What is the confirmatory analysis? Well, one standardizes these last estimate of sigma squared. The large standardized residuals will indicate potential outliers. And the way the analysis then goes is, suppose that m observations have been indicated as being potentially outliers, then the observations have been divided into, tentatively, into n minus m good observations, m bad ones. One then checks this. And to check this, the methods of diagnostic regression analysis can be used. I've already talked a little bit about the ideas of deletion. Here, just check one observation at a time whether, in fact, these are all right. Exactly analogous to the effect of deletion diagnostics, where you look at the effect of removing one observation at a time. Very simple mathematical formulae give one the effect of adding in one observation at a time. These are so-called addition diagnostics, very similar in structure to these. So one can look at the effect of adding back in each of these observations individually that have tentatively. Right, that's then very quick rundown on least median of squares regression and its use coupled with regression diagnostics for finding multiple outliers. What I want to talk about today, having got that introductory material out of the way, is the analysis of transformation. This goes through to a whole lot of other things. I will talk today about the parametric family of power transformations analyzed by Box and Cox in a paper, JRSSB, in 1964. Here is the normalized transformation, the power transformation, y to the lambda minus 1 divided by lambda, so it includes log transformation, the reciprocal, the square root, and of course leaving the data alone, standardized by the geometric mean. Then the hope is that for some lambda to be defined, so this is family of parametric transformations perhaps of the kind with which the previous talk finished, except those will be applied to parameters, that for some lambda there will be a linear model. A simple linear model will be satisfied by the transformed observations. One often hopes, for example, that interaction terms will not be needed once one has got to the correct scale for the analysis of the data. What I shall be concerned today with is testing hypotheses about the value of lambda. Usually the question, of course, is given a set of data, is do I need to transform it? One way of getting a test statistic for this is to expand the model in a Taylor series and then just consider the t-test for regression on this extra variable, the derivative of z of lambda with respect to lambda, a thing which Professor Box, in another paper read to the Royal Statistical Society, called a constructed variable. The approximate score test for this transformation is then just a t-test for adding in an extra variable, the extra constructed variable w, into this linear model. There, for what it's worth, is the test. It's very simple to do. So, I'm going to be concerned then with inference about the transformation in a set of data. There are two tools that I want to look at for my confirmatory analysis. For fixed lambda, I can run a least median of squares regression, and I will describe one way of doing that in just a moment. Then, for fixed lambda, one can look at the effect of deleting one further observation out of the n minus m that appear to be all right by looking at the deletion statistic. One can look at the effect of adding in specific observations that perhaps are outliers by looking at this statistic here. That's for fixed lambda. Alternatively, if one wants to look at the effect on the inference of deleting a particular observation, profile plotted as a function of lambda. So information on all values of lambda, but only for a particular specified subset of the data. So these are two different sections of the space defined by all the observations and the parameters. Right, let's start then to talk about an example. There, for what it's worth, is the statistic. It's just a series of sums and products of residuals of various variables. It's easy to find out the effect of deletion on each of these things and to get a statistic. Here, then, to illustrate the kind of techniques which are available in a set of data, it's regression on a single variable. If just observations 1 to 10 are used in fitting, there is evidence for a transformation. These statistics are approximately standard normal. So this is the test statistic for the hypothesis of no transformation. It has a value of minus 3.4. If one takes a log transformation corresponding to lambda is equal to 0, the statistic has a value of near 0. So the evidence on this line is that the data should be transformed to the log. If a further observation is added, one particular one, it doesn't matter for our present purposes, but it's rather far removed from the rest of the data, outlying in X. This reverses the inference. Now, this is saying there's no evidence for a transformation. You certainly shouldn't do a log transformation. There are a couple more observations too, which have the same effect. In fact, observations 1 to 10 come from a log normal model. The data should be transformed, and that evidence is masked by these three observations here. To reveal that, let me just look first at an index plot of the statistic. This is the approximate score statistic for the hypothesis of a log transformation. The value for all the observations is about 3.5. As individual observations are deleted, the values oscillate between 2.5 and 4.5. So it seems that a log transformation is a satisfactory description of these data. However, we know from looking at this that if in fact one were to somehow to remove observations 11, 12 and 13 from the analysis, then one would get this in which the log transformation would be accepted. So here we have a case where observations 11, 12 and 13 are masked. Individually removing them doesn't have the desired effect. I do, but not with me. I'd like to come back to that at the very end, if I may. It's about the last thing I want to say, actually. Well, one of the properties of least median of squares is it gives rather poor parameter estimates. It gives good information on outliers or by looking at residuals. What I'm going to do now is to look at the residuals of the transformed variable as lambda varies. So a different kind of plot. Now, here we are, different kind of plot. These are standardized least median of squares residuals for a series of transformations. There are 13 data points. I haven't plotted all 13 there. Most of them just run along between about -2 and +2 here and aren't at all interesting. What I have plotted are the residuals which are large over some range of the transformation parameter. And what we see here is that for things like a reciprocal transformation almost up to the log, then observations 11, 12 and 13 most certainly do not fit the model, whereas when we get up here, it seems to be that it's observation 4, when the data are not transformed at all, between 0.1 or 0 and 1. It seems to be observation 10 that is different from the rest. So this shows that there's something different about observation 11, 12, and 13 in one region of the parameter space and 10 in another. And the two ways, as I said, of looking at the conformation, one is one kind of delete 11, 12, and 13 and then look at an index plot of the statistics, and if that is done, what it all is, as it were, revealed. Now, this is fitting the data after I have deleted observations 11, 12, and 13, hence the circles. They show that no evidence for transformation. Deletion of any single further observation leaves the transformation unchanged. Adding back in one of 11, 12, or 13 indicates that the log transformation is not satisfactory. An alternative way of looking at this is to look at plots of the profile log likelihood, and these are a series of profile log likelihoods, Lmax of lambda against lambda, for a series of deletions. When all the observations are in, the maximum is near 1, and it isn't until 11, 12, and 13 have all been deleted that the maximum moves over somewhere nearer to 0. It's a little bit below 0. So if 11, 12, and 13, or even one of them, are in the data set, the maximum is near lambda is equal to 1. Once those three have been deleted, the maximum is near 0. What you might wonder, apart from little computational complexity, is new. Well, this just shows you that least squares won't do the job. This is a plot of the largest least squares residuals against lambda. 11, 12, and 13 are not at all interesting. Their residuals vary between -1 and 0. It's only observation 10 that has at all an appreciable residual as the value of lambda changes. There's a second very simple illustrative example. This is a set of data analyzed some time ago by Box and Cox. There it is, for those of you who work in transformations. What we have is a 3x4 factorial. There are 3 poisons, 4 treatments, 4 replicate observations per cell. The response are survival times of the animals. Here are a variety of score statistics. It's very clear that the data ought to be transformed. The value of the score statistic, as I say, these things are roughly, can be taken as being roughly normal, minus 13.54. For 0, it's minus 4.75. The maximum likelihood estimate of the transformation parameter, that's the point at which the profile log likelihood is, the maximum is minus 0.75. One should, in fact, well, it certainly seems sensible that the data should be analyzed on a reciprocal scale, giving a model which is additive in the rate of death rather than in the time. In order to illustrate the method of robust transformations, David Andrews' paper Biometric in 1973 considered altering observation 20 from 0.23 to 0.13. If that be done, then the score statistic for no transformation is reduced, but it's still quite large. However, that for the log transformation is now close to 0, so is the maximum likelihood estimate of the transformation parameter. As a result of changing this one observation, the log transformation is indicated instead of the inverse transformation. Can we reveal that? Well, if I brought the right pictures with us, we can. Okay. Here's one way of looking at this. Again, I have done least median of squares, regression at a series of values over a grid of 21 values of lambda. These are the large residuals. Again, all the other residuals that I haven't put on this picture lie somewhere in the middle. one can see up here, for the untransformed data, observation 20 doesn't have a very large residual. Some of these other observations do 24, 36, and 21. But as one moves down, going through the log transformation down to the reciprocal, all of these start to agree very nicely with the fitted model. They have small residuals, but the residual of observation 20 becomes extremely large. Another way of looking at this, actually, in this case, single deletion diagnostics do the job very nicely. This is a quick estimate of the transformation parameter calculated from the data that had the log transformation. One can see that the estimate is about, well, a little bit below 0, except when observation 20 is deleted, when suddenly it comes right down to being close to -1. So either of these plots then shows what is going on. They both serve to highlight the importance of observation 20. There were some large residuals for the untransformed data when I started. In fact, they go with these observations here. These are just the largest observations, the survival times 1.24, 1.1, 1.02, and so on. These are the observation numbers, and I think these three turn out to be the three that were the three largest on the plot for lambda is equal to 1. If data should be transformed, then the information on that will often come from the largest observations. You've got a distribution which is skewed to the right. Information about the need for the transformation comes from the largest observations. Similar information, again, comes from looking at profile log likelihood. These are for the altered data. For all the observations, the maximum is near 0, indicating the log transformation. If the two largest, for example, are removed, then the maximum is still near 0, although the evidence for the transformation is reduced as judged by the distance between the height here, and here, likelihood ratio test. When observation 20 is removed, the profile log likelihood has its maximum somewhere near -1. The examples that I've given here are rather simple. They're for illustrative purposes. For example, in Cook and Wang's data, you can get a very good idea of what is going on just by doing a scatter plot of y against x. It's very clear, in fact, that you've got two rather different regimes being obeyed by the data, and that the three observations, 11, 12, and 13, that are causing the difficulty are in a remote part of things. The references to this and other more complicated examples, well, the references are in the abstract, which you all got in the grey book. The paper that will be coming out perhaps in the autumn in the conference proceedings has rather more details of the mathematics. It also has more details on the examples. What I've tried to do is just try to get across the idea of what I'm doing. This, Anders will be pleased to know, is my last transparency as we enter the home straight. So what I've talked about then is a bipartite or two-part approach to data analysis. The first is to use least median of squares for an exploratory analysis, and then down here I have a confirmatory analysis for which I have used least squares regression diagnostics, and in today's talk I have applied these to transformations. An alternative, of course, is to use least median of squares as a starting point for a robust procedure, for example, for M estimation. This leads to automatic downweighting of observations that don't seem to agree with the model. There are dangers in doing this kind of thing, of course. As Professor Hanna mentioned to some of us the other day, the Americans failed to find a hole in the ozone layer because the hole shouldn't be there, and their program therefore trimmed out the data that told them that it was there. Well, Where has he got? It was Australians, wasn't it? Oh, it was Americans, I mean. It was Americans who had this experience? Yes. Yes, okay. Anyway, so what I just want to say is that there are dangers in automatic downweighting. But what you do, whether you go down this route or this route, must, I think, very much depend upon the size of the problem. Well, thank you very much. I do have one last joke about Manchester and Tampere, but I think in view of time, I think.
Thank you for the